Hello, can you hear me? Great. So first, thank you everybody for being here. My name is Ruben Pulido. My colleague is Behar Veliqi. We are both software engineers working for Watson Analytics for social media. And in this talk, we are going to take you on the journey we took from a single tenant Hadoop-based data analytics pipeline to a multi-tenant one based on Apache Spark. So our agenda for today, we will first introduce what is Watson Analytics for social media. We will describe the architecture of our predecessor product. We'll walk you through our thought process on how we became multi-tenant, and we will deep dive in the architecture that allows us to work with multiple tenants, and we'll finalize with some lessons we learned while using Spark in the last year. Okay, so first, Watson Analytics. Watson Analytics is a data analytics solution for business users in the cloud. And within Watson Analytics for social media is an integrated part of it that allows users harvesting and analyzing social media content in order to better understand how products, companies, brands, social issues are being perceived in social media. It targets multiple user groups ranging from customer support to product management, marketing, PR, or even sales. So this is actually how our previous architecture looked like. It was a single tenant and batch oriented, which means we were within each of our phases, we were always processing things in a sequential manner. So the user would enter specific keywords that would determine what subset of the social media data out there was relevant for him. Then we would access multiple sources ranging from Twitter, Facebook, YouTube comments, blog entries, news sites, and crawl that data through access to third data providers. And then we would write that data, the raw data, in HDFS. From there, our MapReduce jobs running in Big Insights, IBM's Hadoop distribution, would read that data and apply text analytics on that. Our text analytics is actually rule-based. And the results were, again, being written back to HDFS. And from there, our machine learning components were analyzing that intermediate output, performing some algorithms on it, for example, to find conversation topics, and then writing those results into HDFS again. And from there, they were consolidated and loaded into DB2. So the business users would access the results through BI dashboards in Cognos. And the main problem that they had is from the time they started a job right here until they could see the results there, they had to wait a really long time. So this was not satisfactory for a customer. And the second problem we had was that because we were a single tenant, for every new customer wanting to use the product, we had to stand up a new cluster. And even though we had quite many clusters, they were most of the time sitting idle while we were not able to accelerate the jobs that tenants were running. So when people think about social media, usually this is the picture they have in mind, huge amounts of data coming at a high rate. And that would actually be ideal for the streaming processing model. But the truth is that if we look at the subset of social media data that is relevant for a specific customer, it actually looks more like that. So it's not a huge stream. So it's rather trickle feed. So a small regular updates of data coming into the system. So a real challenge was how can we efficiently process multiple trickle feeds in an efficient way and within a single system. So we'll walk you now through our thought process towards a new architecture. So the first thing we did was, okay, if we want to change our architecture, we really need to understand what we are exactly doing. So we revisited our analytics workload, and we could identify two types of analytics that we were performing. First, some document-level analytics. And that document-level analytics comprised several parts. The first part was concept detection. Basically, based on the keywords that had been entered by the user, we would detect those in the document content and mark them. the second part, much more interesting one, was not only doing sentiment detection at the document level, but actually trying to associate a specific sentiment with the specific concepts that we had identified in the previous phase. So in that example, product A would get a positive sentiment, whereas product B would get a negative sentiment. And for that, we were applying text analytics rules. The next step of our document level analytics was to extract author features from the document content. So if a user would mention my wife, we would identify him as being married, whereas if in another document he would mention I bought my son a phone, then we would know that he has children. And then, besides document-level analytics, we also had collection-level analytics, as, for example, the creation of author profiles, in which we would consolidate all the author features that we had identified within the previous phase into a single author profile. OK, so once we had better understood our workload, we had to decide what was the best processing model for each of our workload types. So document-level analytics was actually perfect for stream processing. And the benefit of that is that as soon as we had some documents, we could run them through our stream, analyze them, and already present some results to the user. And that was already a big value for them, to start seeing results as soon as the first results were available. The other type of workload we had was collection-level analytics, like consolidation of author profiles or detecting influencers within the set of authors. And for that, you obviously need a batch of documents or possibly all documents in your data set. So the real value there is from the big picture. So we wanted to apply stream processing in a part of our analytics. However, we didn't really have a huge stream. So what we did was, and this was a key finding, was we can aggregate all these small trickle feeds from the different tenants into a single stream, and then process this aggregated stream within a single system in an efficient manner. But for this processing to be efficient, actually, we needed to make sure that all the context switching from analyzing documents from one tenant to analyzing documents from another tenant was done in a very efficient manner. And a prerequisite for that was to break down our analytics into smaller paths, so we could perform different optimizations on them. And we'll see soon what those were. The second aspect was to make sure that we removed all the tenant state from the processing components. So this could be actually stored in a distributed configuration store.
OK. Can you hear me? Yeah, OK. So next, I'm going to talk a little bit about our new architecture that is based on Apache Spark. So basically, from a very high-level perspective, we have multiple tenants over here, or users belonging to multiple tenants. They can basically configure a job on the What's Analytics for Social Media front end. And then the pipeline will fetch the documents according to the configuration from the different third-party providers like Twitter, Facebook, YouTube, etc. And basically, the documents will be pushed through the pipeline, enriched with the extracted data we are able to get, and then upload it to the Watson Analytics platform on the right side. Then the user basically can view the results and create all kinds of different visualizations. So the pipeline itself does not directly communicate with those third-party providers. Rather than that, we have a web service, which we call internally the collection service, which is basically an abstraction layer that provides a unified API to the pipeline itself. So it doesn't have to deal with all kinds of different interfaces from the different providers. Next, the pipeline itself is divided into multiple phases, which are the data fetching part, document analysis part, export, author analysis, and finally the data set creation part. I will go more into details for the different parts later on, but first I want to say that basically the first three parts are processed in parallel. So these ones are being processed using Spark streaming with Apache Kafka, while the last two, the blue ones, are basically using the Spark batch processing APIs on top of HDFS. So the way those phases communicate with each other is basically the following. So whenever a user starts a job, the collection service will create a set of URLs and write them onto the Kafka topic over here. And then the data fetching part will get those URLs, and for every URL, it will send an HTTP request to the collection service, and the collection service in turn will send a response with a batch of documents from the different sources. Then the data fetching part will unify these documents into a common data structure and basically write them onto the next raw topic. From there, the document analysis part will get the raw documents, basically apply all our rules on top of the documents and write them onto the analyzed queue. Then the export part takes the documents as they come in and write them to HDFS. The next step is the author analysis, which is basically a consolidation step that takes all the information we were able to get from the document analysis part and create author profiles. Things like, is the author married, does he have children, and so on. And then finally, the data set creation part takes this result from the HDFS and uploads it, as I said, to the Watson Analytics platform, from where the user can view the results. Okay, so when I say phases, what I actually mean is long-running applications on top of Spark. So every one of these phases is a application running on Spark, which gets started on deployment time, and then it runs all the time until we redeploy a newer version. Besides those 3 stream processing applications and the 2 batch processing applications, we have another application, which is the orchestration application. As Ruben already mentioned, since this is multi-tenant phase and all the jobs are running belonging to different users on the same cluster, we need another orchestration layer that basically keeps track of the different jobs and to show the progress to the user in the front end. I will show more details to this also later. So how is this deployed? Our cluster consists basically of 3 tiers. The first one, the red on the top, is the orchestration tier. Then we have the data processing tier, where the processing itself is actually happening. And then the data storage tier over here, which is an HDFS cluster. So the orchestration tier runs 2 things. First, the Spark masters. So we are using the Spark standalone manager. And second, a Zookeeper ensemble. And on that Zookeeper ensemble, we basically have for every running Watson Analytics of a social media job, a Zookeeper node that stores a bunch of information belonging to that job. So things like, what is the status? Is it running? Is it already completed? Did it fail? If it failed, what's the error code? What is the number of already fetched, already analyzed documents, and so on. Then the data processing part, this is where we run co-located Kafka brokers with the Spark brokers itself. This is where the analysis is applied. And basically, the analysis itself is split into 2 different parts. One is the language-specific part, and the other one is the tenant-specific part. So the language-specific part is basically very heavy. So it is expensive in initialization, and it has quite high memory usage. Thus, it is not appropriate for caching. However, it is basically only language-specific, not tenant-specific. That's why it is stable across tenants. So we can initialize those instances for every language. We do support, like English, German, and so on, when we deploy our application, and then the processing threads from Spark can co-share these instances and use them at the same time. On the other side, the tenant-specific part are very low in memory usage. That's why we can just create something like an Rio cache and cache multiple instances of them in memory. And for that, we have them very low switching overhead when we have incoming documents belonging to different tenants. So comparing this to the previous architecture based on Hadoop, those 2 parts were basically unified into a single part. That's why it was very hard to basically to run multiple jobs belonging to different tenants on the same system. Realizing that we can split this into a heavy language-specific tenant-agnostic part and one tenant-specific part which we can cache allowed us basically to take those trickle feeds, the small feeds, and reunify them into a huge stream like the waterfall shown before. So we can analyze all the documents, no matter to which job and which tenant they belong to, on a single cluster. So the way this looks in code is basically, we have for every topic a direct stream with the Kafka utils from Spark streaming. And for example, here we take the raw documents from the raw topic. Then we apply the analysis on it. So for every micro batch, for every document in the micro batch, we apply the analysis method, which basically uses our extractions rules. Our extractions rules are basically written in AQL, which stands for Annotation Query Language, which is an IBM internal product. I won't go into details here, but basically here is where all the magic happens. Once we have analyzed this micro batch of documents, we will write them into the analyzed queue in Kafka and then update the progress on Zookeeper, so the front end can show the progress tracking part on the user interface. Okay, so we are basically running this setup for almost 1 year in production now. Currently, we have more than 10 active users, running between 150 and up to 300 jobs on a daily basis. Each of these jobs consists of between 25K up to 4 or even 5 million documents. We have currently 3 data centers in Toronto, Dallas, and Amsterdam, each with 10 VMs, and every VM having 16 cores and 32 gigabyte. So with that setup, we are basically able to process up to 60K documents per minute in a mixed workload, so documents from Twitter, from every kind of source. If we run analysis with tweets only, which are much smaller in size, we are even able to analyze up to 150K tweets per minute. So how do we deploy all of this? Our cluster itself is basically wholly Dockerized, so the Spark masters, workers, Zookeeper, Kafka Brook, etc., everything runs on separate Docker containers, and we deploy it via Chef. And then the application itself is basically deployed via this continuous integration pipeline. So whenever we push code to our private GitHub instance, Jenkins job is triggered, which builds an EBO jar containing our newest Scala code, and then a deployment containers build, which contains this EBO jar, besides some deployment utility scripts. The deployment utility scripts basically go through the different Spark masters and check which one of them is the currently active one, and then they use the REST APIs provided by the standalone manager to redeploy the application with the newest code. To do so, it first uploads the newest EBO jar to the HDFS cluster, then it shuts down the currently running application gracefully, and finally redeploys the newest code with the environment-specific configuration. Okay, so that was basically the new architecture. Next, we are going to talk a little bit about the lessons we have learned while running this new stack for almost 1 year in production now. I will try to go to a few of the phases and basically tell what we think is worth telling. So as I already said before, the orchestration part that was on the top of the architecture slide, it does neither use the stream processing API nor the batch processing API, so none of the RDD or dataset API. So why are we running this on Spark at all? Well, basically, if you don't do that, this must be a kind of single source of truth. So there is only one active instance running. If you run it outside of Spark, you would have to run to implement something like a master election you own for a failover mechanism. That's why we basically run this as a driver-only application on top of Spark. If this one crashes, Spark would automatically redeploy it or restart it on another worker. At first, we were very skeptical if this would work, but it seems to be working pretty well since it is running for almost 1 year in production now. Next is the data fetching part, so the first phase of the pipeline. So as I showed before, basically this collection service at the beginning writes a set of URLs to the URLs topic in Kafka, and then the data fetching part would send an HTTP request for every URL. We thought this is basically the best workload for the micro-batch-based stream processing of Apache Spark. However, based on the URL and based on the source, you may get a different batch of documents, a different size of document batches. So it may be 200 documents, it may be 5,000 documents, and these are numbers we cannot set ourselves. That's why it's very hard to basically find an appropriate scheduling delay for the Spark streaming settings. Having that, it almost always leads to high scheduling delays, and it is hard to distribute the workload across the cluster. Also, you can basically not benefit from settings like master partition and back pressure that Spark provides, and also it leads mostly to out-of-memory errors because of the unequal distribution across the cluster. So currently, it's still part of the pipeline, but basically we are thinking, and this is just an evaluation here, to run it outside of Spark as a separate long-running application that basically does this HTTP request and writes the raw documents into Kafka. Then the pipeline itself would only care about the analysis. So input would be raw documents, output analyzed documents. So basically comparing the orchestration part and the data fetching part, for the orchestration part, we were not sure whether this would run fine or not on production. And for the data fetching part, we thought this is basically the perfect workload. However, this one seems to be not working that well, whereas the orchestration part seems to be running pretty well. Okay, so this part is basically about choosing the right Kafka partitioner for our workload in a multi-tenant system. So since we are running a number of jobs in parallel belonging to different tenants, we first thought it might be a good idea to use a job ID partitioner. So every job has a unique job ID. Then we would basically route the documents belonging to one job to a subset of Kafka brokers, and thus they would be processed by a subset of Spark workers. The good thing here is that jobs are run wholly in parallel, and they do not influence each other. However, you have jobs that have maybe 20K or 10K documents, and others with 4 or 5 million documents. So if the red one already finishes, the blue one would not use the resources that are still available on the other workers. So that's why we decided to use a random partitioner. When I say random, what I actually mean is basically you take all the URLs and write them all in equal slices across the Kafka cluster. The good thing is here that the cluster itself is utilized to its fullest. However, when a tenant starts a big job, and maybe a second tenant starts just a small job later on, the jobs would basically be processed sequentially. So this is not really multi-tenant capable. So basically our final solution was, when a tenant starts a job, we would not write the whole set of URLs to Kafka, but rather than that, we would only write a small subset of them to Kafka. And whenever the data fetching phase would basically make an HTTP request, it would return a batch of documents with the next URL. This way, we are utilizing the cluster to its fullest, and jobs run pseudo-parallelly on the cluster. So that was basically the final solution for the partitioning part. Yeah, Ruben.
Okay, the next lesson learned has to do with our last streaming application, which is the exporter, which is basically in charge of reading documents which have been analyzed from Kafka, and then grouping them by job and writing them to HDFS. So our first approach for implementing this Spark app was to use the RDD API and then do the grouping using the Scala Collections API. The problem that this approach had was that when doing the grouping, we were actually using the user memory region of the Spark executor, which is actually not that large, usually only 25% per default of the executor memory. So whenever we had a large batch containing a large amount of documents, then we ran out of memory. So the first workaround that we thought that we could apply to avoid this situation was to reduce the streaming interval. However, when we had to replace the version of this Spark app, then we would shut it down, documents would accumulate in the Kafka topic, and when we started the application again, although the streaming interval was small, we still had a large batch of documents. So we kept running out of memory. So another workaround for that problem is actually setting a hard limit on the amount of documents that can be read per RDD and per partition through the max rate per partition configuration. However, a much better solution than just limiting the rate of documents that we are reading is letting Spark do the grouping and the writing to HDFS. That way, the user memory region is no longer used, but actually the Spark execution memory, which is larger than the user memory region, and has the benefit that Spark manages this region. So if the region is not large enough, Spark can actually borrow memory from the storage region, and if still not large enough, then it will automatically spill to disk and prevent out-of-memory errors. Okay, we have seen before how we could make sure that during our streaming applications, we could process jobs of different sizes in an efficient manner. Now, we are in the author analysis Spark application, which is a batch application that has to basically group all the documents from a specific author and create the author profile. And the situation we run there is that if we had started a large job, then the default scheduler used by Spark is the FIFO scheduler, which means whenever a large job had been already started, a smaller job that would come afterwards would not get any resources allocated to it until all tasks of the bigger job had been completed. Fortunately, there is an easy solution for that problem, since Spark allows setting the fair scheduler. And in that way, tasks are allocated among jobs in a round-robin fashion, and therefore smaller jobs can proceed even when large jobs have been started before. Okay, so with that, we are finished. A short summary on what we cover. We introduced Watson Analytics for social media, a product that allows harvesting and analyzing social media data. We walked through the thought process towards becoming a multi-tenant real-time pipeline, which included splitting our analytics into a smaller path that could be optimized, aggregating all the trickle feeds into a bigger stream, ensuring low latency in context switching between tenants, and removing state from our processing components. And then finally, we presented in detail our new architecture based on Spark, Kafka, and Zookeeper, which is robust, fulfills our latency and throughput requirements, and makes it easy to incorporate additional analytics. So thank you very much for listening.
Thanks for the talk. Very cool architecture. I have one question. Is there a specific reason to choose stand-only deployment of Spark over Spark on Yarn?
Basically, there's no specific. The question is why we are using the standalone Spark manager, right?
Yes, instead of Spark on Yarn.
Okay, actually, we have not really evaluated neither Yarn nor Mesos because we are running only Spark right now. We are not using any other of big data processing engines or whatever. And that was the easiest solution. It is working out pretty well. So why should we choose something more complex than that if it is working fine?
Thanks.
I have a question. As part of the solution, it was suggested that to partition jobs, different jobs into the same node, wouldn't it create a bottleneck, for example, from the memory perspective, or will create a lot of shuffling? Instead of, let's say, sending similar jobs, similar partition to the same node, and then another job partition to another series of nodes.
Okay, so the question is why we use a job ID partitioner?
Yeah.
Basically, we don't. That was what I was trying to bring across. At first, we did, but then we noticed that this is a wrong decision, and that's why we use this later on, this random partitioner with the micro batches always returning next URL to avoid this basically bottleneck you are saying right now. So that was not a suggestion. That was a mistake we did at the beginning.
Was that a question? Or did I answer your question?
Yeah.
Okay. Great.
Okay, thanks.
Any other questions? Anyone? Okay, great. Thank you very much, guys. Thank you.